course you do. Oh.
I come close when I'm speaking, if you don't mind. Hello, everybody. Good afternoon, and welcome to this afternoon session, which we will be starting with Maria Geiser, who has joined us quite recently, isn't that right, as a Sarau postdoc, and is strengthening the pulsar research here in Cape Town. And I guess that's what you will be telling us about. So thank you. Shall I give you after 15 minutes a warning?
I think 15 minutes is all the time I have.
Oh, then I'll give you one at 12.
Okay. Thanks so much. Thanks, Renee. Do we get feedback from online that this is working? Can I just assume it's working?
You can assume it's working.
Okay.
And
for the Zoom people as well, I mean.
You'll be live, and people will get you on the camera and through the microphone, and they'll get to see your...
Perfect. Thanks, Renee, and thanks for the introduction. Like Renee said, I'm working at Sarau, and my research of interest is radio pulsars, and in particular also pulsar timing. And so it's really great to present in person. It's been a while for every one of us, so it's nice to see faces. What I want to tell you about today is how we can use MeerKAT not as a sensitive imaging instrument, but how we can use it as a scale. And if we fine-tune the scale correctly, we can use it to weigh pulsars. And so in particular here, what I'm going to talk about is a pulsar called J0955. And we're going to weigh it and its companion and find that its companion is actually quite a bit lighter than we expected. This work is led by Maciej Cerylak. He used to be a postdoc, he used to work with me in commissioning at Sarau. He's moved to the SKAO now. And the other researchers on this work are all part of the MeerTime collaboration. So MeerTime is the pulsar program running on MeerKAT. And in particular, this is work that we do as part of the relativistic binary project. Okay, so we've got quite a bit to go through. Firstly, what I need to clarify is that I'm saying we're going to weigh pulsars using the MeerKAT scale. And so that can only make sense if we unpack this a little bit. And the point is we'll learn that we can only weigh them if we get to time them. And that means the MeerKAT scale is really being used as a clock. And the reason we can do this is because we're looking at pulsars, and in particular pulsars and binary. So I need to convince you how all these things can come together so that we can get out accurate masses. Now, the first thing that probably was already introduced in this session is that pulsars are incredibly fast rotators. I think in the original version, this is an animation, and so the beam will sweep your line of sight. They are formed whenever you've got a massive star that undergoes gravitational collapse. So you start with a star that's about 10 to 40 times that of the sun. It dies when it's exhausted its fuel, and you're left with this ultra-dense compact object. So the thing spinning in the middle is only about 10 kilometers across. So 10 kilometers in astronomy is a ridiculously small scale. And they spin really fast. And there are also these really intense nuclear laboratories that I can't go into detail. That's kind of a whole talk on its own. But for this talk here, what we want to talk about is not the ones that have just formed and are spinning fast enough, but the ones that are spinning even faster. So you can spin up your standard pulsar to a so-called millisecond pulsar through this process of binary evolution. And so probably many of you are familiar with this. You start with a companion where you've got a massive star and a normal star. The massive star goes supernova, and so you have this first pulsar. And so this first pulsar will go through its whole life cycle, maybe 1 million years. It will emit and will pick up its pulsations, and it will become a cooling neutron star. And after that, we go through the evolution of the other companion object that will overflow its Roche lobe, and it's that accretion process of the material of the companion star falling onto this more dense neutron star that leads us to have pulsars that spin at much faster rates. And so it's really here, it's in this process where I'm accreting matter onto the neutron star, where I'm able to spin it up through this transfer of angular momentum, and now I'm left with a millisecond pulsar that's spinning at a few milliseconds around its own axis. And quite typically, its leftover companion will now be the white dwarf remnant. And so what I want you to think about this here is that if I'm going to care about pulsations where the full duration, the full rotation of the object is a millisecond, and I want to sample these light curves, so to say, then of course I need to really care about sub-millisecond timescales. And you need to put in quite a bit of work to make sure that you are actually able to time things this well. I can see my going from Keynote to PowerPoint has changed some of the fonts, but try and read where they overlap, please. So what we've done for the Meerkat telescope in particular is that we create a time standard right at the telescope. So this is to some extent standard practice. We've got 2 maser-atomic clocks on site, and they generate what we call Kourou telescope time, and that's to within 20 nanoseconds of UTC, and all the data is stamped with those timestamps. And that's kind of good enough for most types of imaging observations, but for pulsar timing, we also have what we call this precise time management system. And so what you saw in the slide is kind of we generate a pulse at the masers, it's sent through the array, and we stop it when it reached back at the masers so that we know what are the extra delays in the system. And so these are things like cable delays, digitizing delays, and by generating these clock files that tell us how we are slightly offset from our original timing, we can come to within 10 nanoseconds of UTC. And so pulsar astronomers really need this extra precision to be able to do their timing experiments. So this slide tries to teach you all the science of pulsar timing in sort of a one slide. And what I want you to take in here is that all we care about is when did the next pulse arrive at my telescope. Can people see cursors? Yep. So at some point, I need to know that the pulse has come to the Meerkat telescope, and there's all these physical processes that can impact on it. So basic things like the pulsar has its own proper motion that will move. Even though the pulses are separated by the pulse period of the pulsar that we learned was like a millisecond or so, this will change over time. So the pulsar slows down over time. So with time, you need to update the pulse period. It won't stay constant. But you need to know, of course, that the Earth goes around the sun. So if I'm here, there will be a delay with respect to whether I'm here. And then the pulse is also traveling through the interstellar medium. And so there's delays even to when you receive it. After it left the pulsar, there will be a frequency-dependent effect imparted on the pulses. So you actually get the high frequencies first and the lower frequencies later, and there's all these time contributions that you have to take care of. Okay, so that's the basic idea. And so in timing modeling, what we say is we have come up with a model that we think is good enough that I literally know every single rotation of the pulsar. So I know that it's going to be pulse number 15,311 arriving because I've taken into account all these processes, and then I actually start observing and I check with my data whether the pulses are indeed arriving where I thought they would be. And here you can see we've made a bit of a mistake. And so it's these little mistakes in our timing that we keep track of. And so here in this example, you can see our model used to be good, and then it got a little bit worse and worse and worse with time. And so if I'm going to plot the differences between when my model expected the pulse to arrive and when it actually arrived, this error will increase across my observing days. And this is a good example of when you have the spin down period of the pulsar incorrectly. So that's the same way as saying the pulse period is, your estimation of the pulse period is getting worse and worse. And so you can see that by analyzing these trends, that's how we get new information. I can now fit a parameter to this curve, and I can remove that effect, and now I've got a good timing model. So when you're doing pulsar astronomy, what you want to see is that between when you expected the pulse to arrive, the pulse with that exact pulse number, and when it arrived, that there's almost no trend, it's just white noise, and the time scales here would typically be something like microseconds. So real precision. So that was it in a slide, but a slide or two, because it gets so much more exciting if this now is a binary. So now I've got all these other extra corrections to my timing. There's the orbital size, there's the fact that as the pulse signal passes its companion due to general relativity, it will be delayed passing through this gravitational well. There's the orientation of the orbit. The orbit can be more circular or more eccentric. And the whole binary can also be moving. So finally, when you're actually timing binary systems, you've got a whole lot more physical quantities that you can estimate from your timing models. Okay, so in this talk, I said I was going to talk about J0955, and that it's an eccentric MSP. So MSP for the fact that it's one of these recycled fast spinning pulsars, and eccentric because its eccentricity is up to about 0.1, and so most binary orbits are very circular, so this is a very elongated orbit. And you can ask, well, why is that strange? And the answer lives in this story we were telling one another about how it evolved. It's in this process of accretion where you expect the whole binary to circularize over time. And you can see that for most binaries that actually holds really well. So here, if you check across different systems with different orbital durations, you can see the eccentricity is very small. The shorter the orbital period, the smaller the eccentricity, and so you have the sense of the orbit having circularized. Except there's these weird outliers, and the system that we're studying is one of them. And so the orbit is weirdly elongated, and we don't exactly understand why. So in this particular study, what we're looking at is 0955, and you can see its companions. It's not a large group at this point. There's only 5 really well understood other eccentric MSPs, and what defines them are these weird elongated orbits, and they also all seem to have roughly similar orbital periods. So the whole binary has a period of about 20 to 30 days. And as I said before, a complete outlier to the typical eccentricities of other binary systems. And so one of the main questions to answer here is, how did that happen? And we won't go into detail here. I've just put up some references, but we'll see later that for this system, we don't think any of these models hold. I'll explain one as an example. If you want to introduce eccentricity into your binary, people think in terms of phase transition models. So you could imagine that if you had a supermassive white dwarf, or with supermassive I just mean more massive than the Chandrasekhar mass, and so that you expect that white dwarf actually to collapse to become the neutron star in your binary, but it's being upheld by the fact that it's rotating really fast, and so you've got this centrifugal forces kind of holding the white dwarf up for longer than expected, and then when it slows down, you have the collapse to the neutron star, and we think that collapse could be one example in which you introduce eccentricity into your system. So here is what the pulsar looks like. It's a very broad pulse shape, and you can see Meerkat and Parkes data. And in pulsar timing, what's really important is for you to have long duration data. So I'm doing that trick now that I showed you earlier, where I'm keeping track of timing residuals. And across 8 years, this is what it looks like. And here you can see the Meerkat data is the really sensitive ones at the end. And like I told you before, you can get out very basic parameters quickly, and this is what pulsar astronomers are also proud of. You can get like the spin frequency up to the 10th or 12th decimal. But I think I'm running out of time, so the bit I really want to get to, because I need to convince you that we can measure masses, is the fact that you can measure these so-called post-Keplerian parameters. And so I think you're all familiar with this idea that Mercury was the system that showed us, or one of the systems that really taught us that general relativity is required for us to have a better description of gravity. And it's because the Mercury orbit precesses, like in my picture here. And so that omega dot, that's about 43 arc seconds per century, you can measure equally in this pulsar system. And once you measure that, you immediately have a constraint on the total mass of the binary. So I now know what's the combined mass of the pulsar and its companion, but I can't yet tell you what the companion mass is. But, and this is really the crux of how we use this as a scale, if you observe this extra delay that the light has to travel passing its companion, you can just about make out this deviation in the timing residuals. Remember, this is the plot that shows me how my model is going a little bit wrong, and it's specifically here a little bit wrong because I've not yet accounted for that effect. And once I fit for that, here that the shape has got 2 parameters, a shape and a range. Once I fit for that, I can constrain both the pulsar mass and the companion mass. And to end, what we find, I'll skip over this, but what we find is that the white dwarf companion is really quite low. It's only 0.25 times the mass of the sun. And the reason this is quite freaky is because if you look at any of the correlations that tell you what the white dwarf mass should be for a given orbital period, you actually expect this low mass to coincide with the orbital period of about 6 days or 14 days, depending on whether you think this is a first population star or a second. And remember, this pulse period was like 24.6 days. So a complete outlier in terms of not fitting the normal white dwarf mass pulse period, orbital period relation. So this is kind of the summary slide. What it? Okay. No problem.
Keep in time. I don't think you can allow any questions now, which is because it was a very nice talk, very interesting. There is a Slack channel, so please either during the next coffee break or send a question on Slack out. We should be happy to respond to that.
Yeah, thanks.
And let's thank Ria. Okay, our next speaker. Oh, it's there we go. Our next speaker is Dr. Monacang from UCT and the SAO. And he will, those of you who have a program that was printed here, it's not the last version, I think. It's on the one that I printed out at home. YouTube is listed here, and he knows he's speaking out, so all was in order. And so he will be speaking about optical and X-ray study of SMC neighbors, those two guys over there. Okay, I'll maybe start waving at 10 minutes so you know where you are.
Is there? Okay, thanks. Thank you very much, Renee. Afternoon, everyone. As you heard, my name is Itumeleng Monacang, and I'll talk to you about some of the research that I've been doing on BE X-ray binaries in the SMC. So I just first want to acknowledge my collaborators who contributed to the work that I'm going to present. So I'll jump right into it by giving a background on BE X-ray binaries. I hope this works. Okay, so this doesn't work. So this was supposed to be a movie showing what's possibly happening in a typical BE X-ray binary star system. So you have the BE star over here with the variable circumstellar disk around its equatorial regions. And you have a compact object, which is generally a neutron star in these systems, that's going around in an eccentric orbit. And if the disk is large enough at close passage of the neutron star, then matter can be accreted by the neutron star, resulting in X-ray activity. And this X-ray activity in these sources is characterized by two types of outburst events. We have type 1 outbursts, which are also called normal outbursts, and we have type 2 outbursts, which are also called giant outbursts. And these are shown here in these example light curves of two well-studied galactic systems. So type 1 outbursts are regular in occurrence when they do occur, and they show low luminosities on the order of about 10 to the 37 x per second. And they're typically separated by the orbital period of the neutron star. So they're associated with the periastron passage or the close passage of the neutron star as it's going around the BE star. Whereas giant outbursts, on the other hand, are called giant outbursts for obvious reasons. They have larger luminosities. So their luminosities are larger than 10 to 37 x per sec. And they appear less frequently. So they're not as frequent when they do happen, not like type 1 outbursts. And they're not associated with any orbital phase. And they also last longer. So these light curves here show extreme cases which can happen in the X-ray binary star system. So for the one case, you have a system that shows a lot of type 1 outbursts and rarely shows type 2 outbursts. Whereas for the other system here, we see lots of type 2 outbursts, but we rarely see type 1 outbursts. But for the most case, we see behavior from these sources that's in between these two extreme cases. And the optical and infrared light from BE X-ray binaries comes primarily from the BE star and disk system. And the observational characteristics in these wavelength regimes is characterized by emission lines and infrared excess. And both of these are the result of the presence of the circumstellar disk. So over here, I'm showing an example of one system that was in two extreme states. So the blue shows when the disk was absent, and the red shows when the disk was present. So you can see that when there is no disk, we see absorption lines in the optical spectra. This is coming from the stellar photosphere. And when the disk is present, we see emission lines in the optical spectra, and we also see infrared excess over here. So in the optical, we see Balmer lines in emission, and we also see some helium lines. But the strongest line that we see in the optical is the H alpha line, which is often used as a tracer of the circumstellar disk variability. And you can see that it can be double peaked, and this is because of the Keplerian distribution of matter in the disk. So the Small Magellanic Cloud, the SMC, which is of course, our neighboring irregular dwarf galaxy, hosts a large number of BE X-ray binaries. In fact, it has a comparable number of BE X-ray binaries with the Milky Way, despite the Milky Way being a few times more massive. And this overabundance of BE X-ray binaries in the SMC is believed to be due to a recent event of star formation that happened due to the tidal interaction between the SMC and the LMC and the Milky Way. So we have this X-ray program, which is called S-Cubed, which monitors the SMC. So S-Cubed stands for Swift SMC Survey. So it's a high cadence and shallow survey of the SMC, which takes snapshots every week, 142 snapshots with 60-second exposure times. So over here, I'm showing an optical image of the SMC with the pointings of S-Cubed. So you can see it covers the full extent of the SMC. And the aim of this program is to both discover and monitor X-ray outbursts that happen, that come from BE X-ray binaries in the SMC. So I'll show some results of two sources that are monitored as part of S-Cubed, SXP 15.3 and 305. So that's the optical image from Ogle and the X-ray image from Chandra. So you can see these objects are quite closely separated. They're separated by only 7.5 arc seconds. And it's this close proximity that has resulted in confusion about the optical counterparts of these sources, since they fall within the X-ray error circles of a few emissions. And actually, SXP 15.3 had its optical companion classified earlier, and it was classified as a B0 main sequence star, which is typical of BE X-ray binaries. And it was noted for the other source, SXP 305, that it showed no emission lines in its optical spectrum. And its spectral type is a bit later than that of SXP 15.3. And thanks to Rosette and Betsy data, we got the 15-second pulse period of SXP 15.3 early, and we also have the orbital period from optical data, which is 75 days. But the pulse period of the other source was elusive for a long time. It's only discovered recently using NuSTAR data. So over here is the X-ray light curve coming from the S-Cube monitoring, coming from the combined region of the two sources. So we see all types of behavior in the X-rays here, where initially we see that it was in a low X-ray state, and then we saw a type 1 outburst here, which was associated with SXP 15.3. And then a few months later, we saw a type 2 outburst, so a giant outburst, again associated with SXP 15.3. And then after that, we saw this series of outbursts from which it wasn't clear from these two sources where it's coming from. So that was the goal of our study, to characterize these outbursts and study where they're coming from. So we followed them up with the Southern African Large Telescope, SALT, and also Ogle to get optical spectra and also optical photometry to study what the disk was doing in both of these sources. So over here, I'm showing the long-term behavior for SXP 15.3. So the bottom panel here is the plot I showed in the previous slide, showing the X-ray behavior. And the top two panels show the H alpha equivalent width and the I-band photometry from Ogle. So as you can see here, at the beginning of the SALT monitoring, it was in a very high state. We measured equivalent widths of around minus 20 angstroms or so, which is the highest reported for this source. And you can see that it corresponds to the beginning of this giant outburst, which in a simple picture suggests that the disk was large enough for a large amount of matter to be accreted, resulting in the giant outburst. And this emission continued to show correlated behavior. So the equivalent width or spectroscopy and the photometry continue to show correlated behavior until we get here to this latest series of outbursts. So the figure here on the right shows a typical profile of the H alpha emission line for this source. So you can see it's a strong single peak profile. And these blue markers here, by the way, indicate epochs when the pulse period was detected for this source. So you can see they correspond to peak X-ray emission here in the light curve. So we did the same for the other source, SSP-15305. So again, the bottom panel is the S-cube light curve, so the X-ray light curve. And that's the ogle I-band photometry during the same time period. And actually, when you look at the long-term photometric behavior of this source, it shows these repeating optical outbursts, which recur every 1,000 days or so, and they last for about 600 days or so. So it appears that the BE disk in this system shows very stable behavior, where the intrinsic variability is quasi-periodic or periodic. So we also got salt spectra for this object. So the first observation here shows the H alpha in absorption. So there was no emission line detected here. And this observation corresponds to the low photometric state here, so just after this latest outburst. And then in the second observation, we saw the H alpha in emission for the first time ever for this source, which confirmed the BE nature of the optical companion. And unfortunately, ogle wasn't available at the time to monitor this part here because of COVID-19 restrictions. But this emission line here suggests that it was undergoing another optical outburst. So it appears that, as you can see here, this latest series of outbursts occur when the source was in a low photometric state, which suggests that, as you can see from the optical spectra, that the disk was absent. So it's unlikely that these outbursts come from this source, but rather they come from the other source, SXP-15.3. We can also get extra information from the multi-filter photometry. So we can use these color magnitude plots to get some more information. So here I'm plotting on the y-axis the brightness or the I-band magnitudes. And then on the x-axis is the color, so the V minus I color. So as you can see, there's a correlation for these two sources between these quantities. And that tells us something about the inclination angle, the BE disk. So for this, in this particular case, it means that the disk had a low inclination angle or intermediate inclination angle, since when the disk grows, we get excess flux. So the system brightens overall, but the color gets redder as well, since the disk is cooler than the BE star. And even within the disk, the outer parts of the disk are cooler than the inner parts. So as the disk grows, the system gets brighter and brighter and also gets redder and redder. For SSP-15.3, we see this interesting looping structure here. And it so happens that the simultaneous V and I band observations were taken during an epoch when there was a disk loss for this source. And it was associated with no X-ray activity. So there was no enhanced X-ray emission coming from this source. So this suggests that the matter was lost from the inside out. So we lost matter from the denser inner regions towards the outer regions, resulting in this loop here. So just to summarize quickly, we monitored two closely separated BE X-ray binary sources in the SMC, where we studied the multi-wavelength behavior in the optical and the X-rays. And we saw that they show very extreme behavior at both wavelengths, and they're very different. The BE disks behaved differently for these sources. And the recent outbursts are likely associated with SSP-15.3 rather than 305, since the disk was absent apparently from the data. And also another interesting thing is that the optical outbursts actually occur at twice the frequency of the X-ray outburst, which is something very interesting, which I don't have time to discuss, but yeah, thanks.
Close to the mic. Thanks very much, Itu. Are there any urgent questions? Can it be answered quickly? Yeah.
Thank you very much. I just want to know which kind of instrumentation you use and method to get your spectra. It's high resolution. It needs high resolution or not?
So
Thank you.
Yeah, thanks for the question. So this was RSS spectra. So it wasn't HRS spectra. So we use general or normal routines of IREF to expect it. Yeah.
I don't see any hands on the Zoom. Is that correct? Okay, then thanks very much. Is Anke not here?
She's online.
Oh, she's online. Okay, let's thank you two again. And I guess our next talk then is online. And that will be Anke van Dijk from SAO and UCT. And she will talk about radio and optical observations of the supernova remnant around SXP 1062. And there she is. Hi, Anke.
Hi, everyone. Oh, apologies for the background. Okay, let me just
Go ahead.
share my screen.
Yeah, great, it's coming.
Are you able to see? All right. Well, good day to you all. My name is Anke van Dijk, and thank you for letting me speak here today at the AfAS conference. I'm speaking on behalf of my collaborators, which is Professor Vanessa McBride and Dr. Tana Joseph, as well as many others. And today I'll be sharing some background with you on this object SXP 1062 and our project, which is still very much in its infancy, and a project which is quite new to me, and just looking at some of the exciting work that we have planned for the future. So SXP 1062 is located in the Small Magellanic Cloud. And this is a system called the BE X-ray binary, which you might have heard in the previous talk. And this is a subsystem of what is classified as high mass X-ray binaries. And it consists of an X-ray pulsar that is accreting material from the circumstellar disk of a companion star, which is in this case an early B0 type star. And this system is interesting because of its unusually long spin period of 1,062 seconds. And there are very few such systems which exceed spin periods of 1,000 seconds. And it really challenges our understanding of neutron star formation and pulsar evolution. So the current evolutionary model of neutron stars and pulsars look a little bit something like this. So you have your neutron star, which is formed as a result of the supernova explosion of a very massive star, typically something between 10 and 20 solar masses. And it is born with a very rapid rotation along the lines of 10 milliseconds. And as the system evolves, the neutron star spin is it's slowing down, so the rotational period is increasing due to effects such as magnetic dipole breaking, propeller effects from the magnetic field within the binary, as well as mass loss from the companion star. So when the rotation is sufficiently slow, then only can accretion from the companion onto the neutron star occur, at which point it will be detected in the X-ray. Now, this picture really is highly dependent on many initial conditions, such as the magnetic field strength around the neutron star, and then later on the mass accretion rate from the companion onto the compact object. But the current thinking is that the time scale for a high mass or for an X-ray binary to form post supernova explosion is around the 10 millennia mark. So you have something that looks like this, where you start off with a very rapid rotation spin period, and then it slows the system down, at which point the magnetosphere radius becomes equal to the co-rotation radius of the system, and then only can material penetrate and accrete onto the neutron star system. So at this point, at the equilibrium point, the spin periods tend to be in the region of 1 to 100 seconds with very strong magnetic fields. So in a paper written last year by Gvaramadze et al., where they used salt long slit spectra to map velocities of the diffuse emission in this supernova remnant shell along the slit around SXP 1062. And really, here comes the crux of the situation, is that the age determination of the supernova remnant suggests that the system must be far younger than what we know or what we think from the evolutionary model of pulsars. And it has been suggested that the supernova remnant is very likely less than 10,000 years old, estimated by various people. So here it shows the M-cells image on the left in various filters, where you can see the supernova remnant shell and a central point source. And on the right is the Meerkat radio image that shows a very, very faint supernova remnant in amazing resolution. But you can see that there is no central pulsar or point source detected in the radio. So something like population synthesis may provide a window into some of these, into this strange system to sort of model where we can see that mass accretion onto the compact object ensues before the supernova remnant has dissipated. And really, we're asking the type of question saying that, is the system much younger than we believed? Has this binary undergone some sort of rapid evolution, and why? Another theory has also been brought forward that the spin velocity at the birth of the neutron star could also be significantly higher than current modeling suggests. So here I show a compact object. I show a composite image of the M-cells image, where it shows the optical and also combined with the radio image. And you can see there's almost a sort of anti-correlated. And our salt data that we got is also a long slit spectra that is at several different position angles that traces the diffuse emission also along the shell. And really the idea with this is that mapping the ejecta of the supernova remnant, will provide a clearer picture of what is going on in the system in terms of the speed that the shell is expanding, and hopefully, while attempting to reconcile it with what is going on with the central pulsar. Additionally, the radio observations will allow us to characterize the emission mechanism in the diffuse gas by getting the spectral index that differentiates obviously between thermal or synchrotron emission. And that is more or less that lies forward for us, and very, very exciting new project. Thank you very much.
Thanks very much, Anke, and also for keeping to time. We're back on schedule. Are there any questions for Anke or ideas, given that she's working on this exciting project? Yes, David, can you the microphone is coming to you.
Yeah, these long
David
period
Buckley.
systems are certainly quite interesting. I think there's only about 4 or 5 of them known. I was aware of some attempts to explain the anomalous long periods without invoking massive magnetic fields that might be hard to explain evolutionarily. And there was a model put forward by a Russian group which was basically using the idea of magnetized wind accretion rather than conventional disk accretion in these systems. I don't know whether that's something that you're aware of, or whether this is something to look at in the study of this system and potentially others.
Yes, thanks, David. Yeah, no, obviously I'm quite new to this, so that's definitely something to look at in the future. Thanks.
Anything else? I don't know, Anke, can you probably see easier? Is there somebody who has a hand up on the Zoom?
Not that I can tell, no.
Okay, then I think there's no further questions. So thanks very much for that, Anke.
Thank you.
Okay, then our next speaker is AfAS from University of Science and Technology. And I think he needs an applause already to start his talk, because as you can see on the program, he is one of the 2021 AfAS Early Career Research Grant recipient. Congratulations. I guess the work that you got your grant for is what you're going to talk about. Is that correct? We'll be talking about the work that you got your grant for, or that was awarded for, or is this already a new research project?
Projects we are doing.
That you're going to do now. Okay, good. I'll wave after 10 minutes so you know that there's 2 or 3 more minutes to go. Okay?
Okay, thank you. Good afternoon, everyone. I'm Trust Otto from Mbarara University of Science and Technology, Uganda. We are working on a number of projects, and this is one of them. Our main interest are the intermediate mass stars, which lie in this region along the main sequence. These stars have interesting phenomena which include the pulsations. As we can see, they have magnetic fields and also rotation. Then they also have chemical peculiarities, because that is where we find the AM stars and the AP stars. So the chemical peculiar stars have overbalances of metallic elements and underbalances of the weak elements, the light elements like calcium and scandium. So for this particular star, was in the catalog of Ransom 2009, and it was suspected to be an AM star, though it wasn't confirmed. Then it was later studied by Barona 2015, and it was thought to be a rotational variable. Then it was studied again by Catanzaro 2015 and 2019. It was thought to be a pulsator. So what we did, we obtained the test data for this star. It was observed in sector 14, sector 15, and sector 26. And these are the only signals we could find within the zoom-in regions. But we could not find any pulsation. And we realized these could be rotational frequencies. So to confirm that, we performed a wavelet analysis, which is here, monitoring these frequencies in a given period of time, and realized that still these frequencies are rotational. Even from the autocorrelation of the light curve, we see a maximum here and a lower maximum, which signifies the presence of a spot, a main spot, then another weak spot, which is diametrically opposite to the major spot. Then from the autocorrelation, the composite spectrum, we realized that the actual rotational period of this star is 4.1, around 4.1 days, while the other approximates to be the harmonic. So after doing that, we observed this star in 2018 and obtained its spectrum with high resolution, performed all the basic processing of the data, and then performed spectral classification. But for spectral classification, we could not obtain a spectra for the standard stars. So what we did, we used the already available standard libraries, but the characteristics are different from the spectrum we obtained from Hermes spectrograph. So we had to pre-process the Hermes data. For example, reducing the wavelength to suit the wavelength of the standard library, then also reducing the resolution. So after doing all that, we compared the Hermes spectrum with that of the standard libraries, and realized that for the calcium K line, the spectrotype is A1, while the hydrogen lines show that the spectrotype is A8, and the metallic lines, the spectrotype is also A8. So these spectrotypes being different, it signifies that this star is chemically peculiar. Now, to confirm that further, we were supposed to perform individual chemical analysis. In order to do that, we had to obtain the atmospheric parameters. And to do that, we obtained the initial gas from the said analysis. We obtained the spectrophometric data from these databases, and performed the spectral synthesis analysis and obtained the parameters of this star. These are the parameters we obtained from spectroscopy. The luminosity was from the Gaia parallaxes, radius from the Stefan's law, the after getting all the rotation period, we are also able to get the inclination angle, mass and age were from evolutionary track fitting and isochron fitting. Those were just extra parameters. Then after getting all those parameters, we obtained the abundances by fitting the Hermes spectrum for each element. And we realized that indeed the calcium and scandium are underabundant, while the heavy elements are overabundant. While doing all this abundance analysis, we assumed a local thermodynamic equilibrium. So to make sure that the effects of non-local thermodynamic equilibrium are also catered for, or whether they are not there, we performed NLTE analysis for calcium and realized that the difference in the results is small and lies within the error margin. Our comparison with the available results in the literature is okay and good. We managed to put this star in the HR diagram, and that is the location where the rest of our stars of interest lie. Then the conclusions is that this star is a rotational variable and not a pulsator, and it is an AM star with this spectrotype. Then similar works, we have also looked at hump and spike stars. These stars have humps and spikes within their frequency spectra. They are very, very interesting stars. So we can also go there and check on them out. Then in this paper, we made a very significant and interesting discovery where we found a heartbeat star, which is also chemically peculiar, which is the first of its kind. Acknowledgements, acknowledge ISP and AfAS for funding. Kepler and the TESS, Hermes and VOSA teams. Professor Don Katz for discussions and whatnot. Professor Vadim Lyudmila for the non-LTE discussions. Thank you for listening.
Okay, it is a nice talk. Thank you. One of your parameters error is it is about 38% like that. Maybe R.
Sorry?
Maybe the radius, or I don't know if you go to your slide from 0.8 plus minus 0.18. It is bigger.
Yeah.
Okay.
Yeah, radius. The uncertainty is high. Mass and yeah, because of the method we use, and this star is not a binary, so it is quite not easy to well constrain the mass and radius.
Okay, Don?
Otto, I think we've talked about this before, but the best explanation for your variations there are not rotational from spots, but are from R modes, which we know are ubiquitous across the upper main sequence. and that will give you a slightly longer rotation period. Your two groups are nicely fit with different degrees of R modes. And if you look at the work that Hideyuki Sayo and I and others have been doing over the last few years, you'll find that that hypothesis, which in fact is more physical than the spots, since we understand the physics of the R modes, will give you a better explanation of what you're seeing with a slight shift in your frequency, and that'll change some of your derived parameters.
Yes, for the hump and spike, the reason is the R modes, as you state. But for this particular star, we don't have the hump and spike features in it. Yeah.
Okay, looks like there's going to be more discussion in the tea break. Any further questions? I don't see any hands up there on the screen. No? Let's thank Otto again. And we did catch up a bit on time. If there's still a question for Maria now, there is still